Hello and good morning to everyone. This is Mr. Hill again with some more science. We're going to talk about KMT, which stands for Kinetic Molecular Theory and Solubility. All right, here's a review we're going to do with solutions thus far. A homogeneous solution, or first of all, solution is a homogeneous mixture of a solute dissolved in a solvent. A solute, of course, is the compound. May it be uh, thick, like a oil or even a powder substance or something that is a solid or dry substance like salt, sugar, for example, even flour. And then it's dissolved in the solvent is the liquid or what we call water or aqueous, a water like solution. The solubility, the ability to dissolve of a solute in a solvent is dependent on the, and that should be on the properties of the material. And I will fix that. Temperature in particular. You have for solids, the solute, as the temperature increases, the solubility increases. For gases, the temperature is going to be an opposite. As the temperature increases, the solubility decreases. So therefore, as the temperature decreases, the solubility increases because a gas is already at a state that is a level three state of matter because fourth level is plasma where it has so much energy it glows and gives off radiation like our sun. Our sun is a nuclear reactor. It does in itself exist in the fourth state of matter, at least as far as we know. So again, we need to have things where the temperatures for solids and liquids will make it where solubility is increased and temperature increase. Gases work the opposite. Now for pressure, also went with pressure in itself. For solids, the solute itself, the pressure increases, the solubility remains the same. With gases, the solubility increases because the pressure helps make the gas confined to a space to become an actual solid. There were experiments done about 25, 30 years ago where you can take, for example, hydrogen gas in a industrial strength cubit, which is a, a long rectangular tube that you can put the gas in, and you can use a machine that put pressure on it up to, I believe, 1 atmosphere or 1 atm, or it was somewhere around 1.5 atm. And it'll put it under the pressure to make it where it would be a liquid under those conditions, and of course, only for a matter of a few seconds, so you won't break the cubit. Also, the nature of the solute solvent is where simply like dissolves in the like, and yeah, like attracts like as well. Because if you do have a nonpolar compound mixed into a nonpolar liquid, it will dissolve very well. Just as if you have a polar compound in a polar liquid, it will also dissolve very well. It's just that when you have the two things that are opposite in polarity, where you have a nonpolar liquid trying to dissolve a polar compound. That's not going to work very well. Like, for example, water and oil is not going to mix very well. You can mix it with machinery, but over time, it will actually start to separate. All right. Solubility summary in itself. Here's a breakdown of it. A solute type, nonpolar solvent, you have a polar solvent. So if we look at the breakdown here for a solute type, we'll look at nonpolar, like fat or grease. I'm going from left to right. That is soluble. Uh, Fat or grease is non-polar, and so in a non-polar solvent, it will actually be soluble, like soap, for example. And then a polar uh, solvent is insoluble, like water. And there's a reason why fat and soap are like that because when you take a bath, for example, the soap molecule binds on one end to the grease or the dirt in your skin, if you will, or it's called soil. And then on the opposite side of that water molecule, when a soap molecule, it bonds with water or H2O. And so when you take a shower and the water runs down your body with soap, the soap literally pulls the dirt off your body and down the drain as a result. And we look at polar types. It is insoluble in a non-polar solvent, but it is very much soluble in a polar solvent. And if you look at ionic types, which is a salt, It's insoluble in a non-polar solvent, but it's soluble in a water-like solvent. So therefore, we go in with solubilities based on the types of compounds in itself. Also, let's review the different types of saturated or saturation states, if you will, of solutions. Unsaturated means that the solution itself is actually more than able to dissolve the solvent. And then if you have a saturated solution, for example, it is a solution that contains the maximum amount of solute and solvent. In other words, they break even. So you can't really put no more in there. It's just enough solvent to dissolve. We dissolve with enough solute. They're just breaking even to be exact. Then supersaturated means that you have more solute than would dissolve in the solvent. And examples of that would be when you buy fruit juice concentrate from the store. If you go in the freezer section and you see the round cylinder that is, I believe, 16 ounces, or sometimes comes as 12 ounces, like Welch's grape juice, or if you go to Kroger's or any other name brand store, they have their version of grape juice, apple juice, orange juice, mango juice, even some companies like High C Fruit Punch or Hawaiian Punch. They make a concentrate you can buy in a canister or a plastic bottle at Gordon Foods. And what it is that it is to be dissolved in water. It is a super sugary substance. If you try to drink it, it can make you sick. So you do have to have water to it so it can taste in such a way you can digest properly. And for those who like to do uh, dares, do not try that at home. I repeat, do not try that at home. Also, more of the review solubility rules. Not all ionic compounds are water soluble. There are some general rules for compounds that are water soluble. And if we look at it, group one on the periodic table, compounds and ammonium, NH4, are always soluble in water. Whereas group 17 ionic compounds, meaning that these are compounds made with ionic elements, to be exact, or elements that form ionic compounds. And the better way to put it, are water soluble except for those with um, silver, lead, and mercury. Also, you can see table F, which is associated with periodic table, and I'll actually get that table available to you all very soon for other rules and exceptions. Also, here's more examples of water solubility as well. We have silver nitrate, the water soluble. You also have silver chloride, and you have NaS, so Na2S, which is sodium sulfide, and then we have sodium chloride soluble. And my apologies, silver chloride is not soluble; it's insoluble, just like calcium carbonate, CaCO3, is insoluble, and then aluminum phosphate, or phosphate, excuse me, is insoluble as well. AlPO4. The concentrations of solutions in itself are based on the sense of homogeneous, meaning that the mixture is mixed together where it looks like one solid mixture with nothing in it. So examples of that would be chocolate syrup, milk, unless you're drinking whole milk, and even like strawberry syrup, like Nestle Quick. Those are examples of homogeneous mixtures where you can't see what's really mixed into it. It's not like Italian dressing, for example. You can see the spices, you can see different colors and other things mixed into the dressing itself. And sometimes it is inadequate to refer to a solution as a diluted or dilute or concentrate. And that's because of the fact that it deals with how much you're starting with. And so, therefore, they are what they call qualitative descriptions of concentrations that actually describes how much of something is in a solution for itself. So, here's an idea. This gets more towards chemistry to really think about it. If you get a solution, like, for example, rubbing alcohol, you'll see things in there say 70%, 80%, maybe even 90% alcohol, or in some cases, 60%. That lets us know that 60% of that bottle is isopropyl alcohol. The rest of it is purified water. But if you did a science experiment using 60% alcohol in itself, that would technically be your 100% concentration for your experiment. So just keep in mind that concentrations will vary based on the descriptions and what you have available. Here are some things dealing with the kinetic molecular theory, and here's the reason why. Kinetic molecular theory does deal with the way things dissolve or separate or dissociate. Those are three different terms we've seen so far, which means when you mix a solute, a compound, into a solvent, it's going to break up and dissolve in it if it's able to do so. And you have kinetic molecular theory that gets into that situation there. So the first rule of it is that matter is composed of tiny particles, atoms, molecules, ions, that have a definite and characteristic size that do not change. So in other words, everything's made of tiny particles is the way to think of it. The second one is that these particles are in constant random motion. So it possesses kinetic energy. Kinetic energy, if you remember from last year, is the energy that matter possesses because of its motion, if you will. A runner in the Olympics, if you're on the track field, has kinetic energy because they're running, if you will. And also, number three is that the particles interact with one another through the attraction and repulsion. So, therefore, you have particles that are attracted to one to another, depending on how the electrons on the outside spin. So, you have attraction and repulsion going on, so pushing and pulling, if you will. And we know about that dealing with the polarity of compounds, like nonpolar compounds, meaning that there's an even share, and polar compounds means that there one element is going to be stronger than the other, like HCl. We know that HCl theoretically is going to have it where the chlorine is going to have a 7 times stronger pull than the hydrogen atom because of the fact that there's seven more electrons there's seven electrons, excuse me, with chlorine than it is with the hydrogen atom makes up the HCl in itself. So we look at things such as potential energy, stored energy that a matter possesses as a result of its position, condition, or its composition. So we know that uh, there's a certain amount of energy that's stored with sodium and chlorine right before they mix together because of the explosion that happens when you form table salt. And then what's called electrostatic interaction is the attraction or repulsion occurs between particles. In other words, it's is the point where things can pull or push each other away with little energy or a lot of energy based on how much of electric charge or electric static charge is available. So think about static electricity. The more you rub your feet on the carpet, for example, the higher the discharge it will be when you touch your brother or sister on your shoulder. And by the way, do not do that at home. Do not do that at home because it's not good. Here's a better example. If you take a comb and you comb your hair quickly through your head, easily, don't hurt your scalp, and you let the water run in the sink where it's like a thin streaming line, and you put the comb near the stream, it will actually make the water bend, if you will, because the repulsion. And when you pull away the comb, it will actually bring the bend that's in the water to come back. That is an example of electrostatic interaction. So that way you can see it for yourself at home. And we may look into that a little bit later in the lesson, maybe this week and next week. All right, the kinetic energy or velocity of a particles increase as the temperature increases. So here we are. We can start to see now why kinetic molecular theory is a part of uh, solubility because how well something can dissolve. Like dissolves in like. So nonpolar is going to dissolve in nonpolar, and polar is going to dissolve in polar. So nonpolar, if I have a nonpolar compound dissolving in something that's non-polar because they all share evenly, they're going to actually do that a lot faster. The temperature increases in itself. And the opposite is true. If it does not dissolve and it makes crystals or cause things to actually produce a precipitate, at the bottom it's going to happen a lot quicker as well. Because again, it's going to speed up those collisions, how fast things interact and bombard, if you will. Just like if you take a shower in the morning, the hot water is going to help the soap begin to lather on your body, and it's going to help cause the bonding of the soap molecule with the dirt on one end and with the water on the other end to happen a lot sooner than it would if it wasn't. And these particles, for number five, for kinetic molecular theory, has it where energy is transferred from particle to particle through what they call elastic collisions. Elastic collisions means that you collide with something and it comes back to where it started. So it's like if you Think about a what's called a tether ball. Tether ball is nothing but a ball on a string, and you can use a tether ball to practice. T-ball is sometimes called in baseball, but tether ball can be used to help you practice with badminton and tennis. It's nothing but a ball on a string, and you hit it, and the ball's job on the string is to move away from you. Whatever force you apply to it, come back to you to have another collision over and over again. So that's what I mean by elastic collisions. All right, KMT of matter related solubility. Here's the breakdown of it all. As the temperature of a solution is increased, the average kinetic energy of the molecules, ions, atoms that make up the solution also increase. So that means that the kinetic energy allows the solvent molecules to be more effective in breaking apart and actually being or coming together. And it's by what's called intermolecular attraction. Intermolecular, we talked about this 2 weeks ago, meaning that it is the overall attractions with inside the compound or the molecule of that compound. So that's what the intermolecular, international means all nations or all national, if you will, international. So if I want to travel the world, they'll say you want to be international. You want to go all over to all nations, if you will. So overall, throughout the entire molecule itself, there are forces that hold the molecule together. All right. Classwork assignment. Do the collisions within dissolving assignment. I also have quiz one on Friday, which would be the 4th of December 2020. I do apologize from yesterday that I didn't state what the quiz is going to be on. It's going to be on ionic covalent compounds and bonds. It'll be like the questions you all had in the previous weeks. So it's not going to be something that's based on new material because we're going to go a little bit more in depth with this material to keep confusion down. Again, send me any questions through Schoology or you can email me, and therefore we'll go from there. Thank you, and you definitely have a great day.